little bit of terminology, and I'll just kind of slip in a box down here. What I'm saying is that now what we've done here we maximize a function t subject to a constraint, and that constraint is f of x, y, z equals 0, meaning in the context of this example and in context of the temperature interpretation, we maximize the temperature subject to the constraint that we're somewhere on a given surface in space. So we find the maximum or minimum value of the temperature function on that surface. Temperature function is given in 3 dimensions, but the surface constrains you to a 2-dimensional surface. Now let's consider an example where we actually apply this to a function and a constraint. Let's consider a sphere, and let's let that sphere just have radius 1. And let's suppose there's a temperature function within this sphere. It's a function of r, your distance from the center, just equal to 1 over 1 plus r. Now, we probably don't want to do our partial derivatives in coordinates where r is one of our coordinates. So we're going to do this in x, y, z coordinates, and r, let's just assume the center of this thing is at the origin, so that r is is the square root of x squared plus y squared plus z squared. Now the main reason I have the 1 in here is so that the denominator can't equal 0, because of course then our function would not be defined even at x equals 0, and we certainly wouldn't have continuous derivatives, so we wouldn't want to consider that function. Another option would be to just let t of r be 1 over r and restrict r so that it can't be 0. In any case, we could use this temperature function. Now, the maximum of x squared plus y squared plus z squared is going to be 1 within this sphere because the radius is 1. Now, this isn't really what I intended to do, but we understand the argument I made. I'm going to make a slight change in this. I'm going to let t of x, y, z equal 1 over the square root of 1 plus x squared plus y squared plus z squared. Get that 1 inside the square root. There's a good reason for that. Just because of the algebra that we'll be facing, I'd rather do this than this. This would be a little longer than this, and the algebra would be a little more difficult to understand. So I'm going to cross this function out, and I'm going to maximize this one. The constraint I want to use is, let me draw this in x, y, z space. We know that the sphere would come out a unit distance on each axis. So if these marks represent unit distances along the axis, I want to do the plane that's defined by this triangle. So that my constraint is that the point x, y, z lie on this plane someplace. And in fact, just to make it a little more interesting, let's let x, y, z lie on this actual triangle. Take that back. We're going to just do the plane so we don't have to worry about boundaries. The maximum is going to occur in any case at a point that's on the triangle. Okay, so the constraint is going to be that we're on the plane. Now that plane is x plus y plus z equals 1. So we're maximizing this expression subject to this relatively simple constraint. Now, this constraint is of the form f of x, y, z equals 0, where f of x, y, z is x plus y plus z minus 1. The f of x, y, z equals 0 means x plus y plus z minus 1 is 0, meaning that x plus y plus z would be 1. So having put the problem into the terminology that we were using here, we see that this is going to occur when the gradient of the t function is parallel to the gradient of the f function. It's going to give us these equations, which we're going to try to solve for lambda and x, y, z, and our constraint function f of x, y, z equals 0, giving us 4 equations and 4 unknowns. The gradient of our f function is easy enough, so well, let's write down the condition again. That's going to be gradient of t equals lambda times the gradient of f, meaning that the gradient of t is parallel to the gradient of f if there's a constant lambda. It makes this so. Now the gradient of f is really easy. That's fxi plus fyj plus fzk, and fx is just 1, fy is 1, fz is 1, so that del f is just I plus j plus k. And we usually don't have such a nice del f function, but in this case the del f is kind of nice and simple and cooperative. Now del t is txi plus tyj plus tzk. Now x, y, and z all appear in the same form in this denominator. So if we can just take the derivative of one of our t function with respect to one of the variables, it'll be pretty easy to write down the derivative with respect to the others. However, our t function is a reciprocal of a square root of something that involves squares, which means it's a somewhat involved composite, so we're going to need more room than we have right here. I'm going to use another piece of paper. So what we want is we want the derivative, partial derivative, with respect to x of 1 over the square root of 1 plus x squared plus y squared plus z squared. Now, we can write that as partial with respect to x of 1 plus x squared plus y squared plus z squared to the negative 1/2. Just using the power function notation eliminates one of the steps in the composite, reciprocal of square root of. And now we just have power function of. That derivative will be negative 1/2 times the partial with respect to x of the inner function 1 plus x squared plus y squared plus z squared, multiplied by the original function to one less power. That would be the negative 3/2 power, 1 plus x squared plus y squared plus z squared to the negative 3/2. The partial with respect to x here is just 2x, so that's pretty easy. So this much of our expression is just going to be 2x, and that's going to be multiplied by negative 1/2. So that comes out actually fairly neatly as negative x times 1 plus x squared plus y squared plus z squared to the negative 3/2. Now, without going through the details, I'll simply assert, and you can follow the same steps, the same sequence of reasoning that we used here. The partial with respect to y of 1 over the square root of 1 plus x squared plus y squared plus z squared is negative y times 1 plus x squared plus y squared plus z squared to the negative 3/2, and the partial with respect to z of the same expression is negative z times 1 plus x squared plus y squared plus z squared to the negative 3/2. Now, I'm not sure that you were able to see the edges of this paper, but there's our expression. These are the expressions for the three partial derivatives. Using these three expressions, we see that del t, which is txi plus tyj plus tzk, can be written. Well, we're going to add these three expressions, and each expression has this negative 3/2 power as a factor. So I'm simply going to factor those three out, and what do we have left? We have negative x, negative y, and negative z. So the algebra of this becomes relatively simple. We have negative x I, negative yj, minus zk, multiplied by the 1 plus x squared plus y squared plus z squared to the 3/2 power. Not sure that 3 is going to be all that legible. And we could write that as, if we wish, negative xi minus yj minus zk over the quantity 1 plus x squared plus y squared plus z squared raised to the 3/2. Now that we have our expressions for del t and del f, we can set them equal, get our four equations, solve for lambda x, y, z, and see where this temperature function will maximize.